Hello everyone, I'm Mehdi and today let's get into atomic structure and interatomic bonding. When we think about atoms, we are not just talking about tiny particles floating around. The way they bond with each other changes everything about the materials we use. First, let's think about what makes atoms want to bond. Atoms are kind of like people. They want to feel complete or stable. So, when their outer shell of electrons is not full, they are like someone who is looking for a partner to feel balanced. They either share, give, or take electrons to fill that outer shell. Exactly, they bond to achieve stability. Now, when we look at the types of bonds that form between atoms, we can break them down into a few main categories. First, we have got ionic bonds. This happens when one atom gives up an electron and another takes it. Next up, we have covalent bonds. These happen when atoms share electrons. It's like two people holding hands. Each atom holds onto the shared electron tightly. Diamond is a great example of a material held together by strong covalent bonds, which is why it is one of the hardest materials out there. Now let's move on to metallic bonds. Metals are interesting because their electrons are free to move around. This sea of electrons gives metals their shiny appearance and make them great conductors of electricity and heat. Why do you think metals, like copper or aluminum, conduct electricity so well? They are weaker bonds that happen between molecules. So they are more like people standing near each other at a party rather than holding hands. They are important in materials like graphite or plastics, where the layers or molecules are loosely bonded together, making them soft or slippery. Alright, let's break down the basics of atomic structure. Every material is made up of atoms, but what exactly are these atoms made of? Well, we have got three main building blocks: electrons, protons, and neutrons. Starting with electrons, these are the tiny negatively charged particles that zoom around the nucleus of the atom. They are incredibly small. Now, protons and neutrons live in the nucleus, and they are much heavier. Protons and neutrons both weigh around 1.67 times 10 to the negative 27 kilogram. So, protons are positively charged, neutrons have no charge, and electrons are negatively charged. Now let's talk about the atomic number. This is the number of protons in the nucleus of an atom. And in a neutral atom, it also equals the number of electrons. For example, carbon has an atomic number of 6, meaning it has 6 protons and electrons. The atomic number tells us a lot about the element's identity and its position on the periodic table. Now, onto atomic mass. This is where things get interesting. Atomic mass is usually measured in atomic mass units, AMU. We define 1 AMU as 1 over 12, the mass of a carbon-12 atom. So, when we say carbon's atomic mass is 12, we are saying that one carbon atom weighs roughly 12 AMU. A cool thing about atomic mass is that it is directly related to moles. 1 mole of any element contains 6.022 times 10 to the 23 atoms or molecules. This is called Avogadro's number. So when we say 1 AMU per atom equals 1 gram per mole. So we are saying that if you have 1 mole of atoms, its mass in grams will equal its atomic mass in AMU. Now, what we understand the basic structure of an atom, let's talk about how that structure affects some of the key properties of materials. It's all about the electronic structure, how the electrons are arranged around the nucleus. This arrangement can determine a material's behavior in a few different ways: chemical, electrical, thermal, and optical. Let's start with the chemical properties. The way atoms bond and interact with other atoms depends entirely on their electron configuration, specifically the electrons in the outer shell, which we call valence electrons. These are the electrons involved in bonding. For example, when sodium and chlorine bonds to form salt, it's the electron transfer between these two atoms that drives the chemical reaction. Now we have electrical properties. If we are talking about materials like metals, their ability to conduct electricity comes down to the movement of electrons. In metals, electrons are free to move, which is why they conduct electricity so well. On the other hand, materials like rubber don't have free electrons, so they act as insulators. Moving on to thermal properties, atoms in a material are constantly vibrating, and when you heat something up, you are essentially increasing the vibration of those atoms. Materials with a lot of free electrons, like metals, not only conduct electricity well, but also conduct heat efficiently. That's why metal objects get hot quickly when placed near a heat source, while something like wood does not. Lastly, we have optical properties. The way light interacts with a material depends on how its electrons absorb and emit energy. For example, when light hits certain materials, the electron can get excited and jump to higher energy levels. This is why materials like glass are transparent while metal reflect light. So, whether we are talking about how a material reacts with chemicals, conducts electricity, transfer heats, or interact with light, it all boils down to the electronic structure of the atoms. Well, let's focus deeper into the electronic structure of atoms. What is really fascinating about electrons is that they have both wave-like and particle-like characteristics. This duality is one of the weirdest concepts in quantum mechanics. So, we cannot exactly pinpoint where an electron is, but we can talk about its probability density, which tells us where it is most likely to be. Think of it like this, rather than imagine, electrons as a little balls orbiting around the nucleus. It's better to think of them as waves that exist in a kind of cloud around the nucleus. The shape, size, and orientation of this cloud or probability density is determined by something called quantum numbers. These quantum numbers are like an address for the electron. They tell us where it can be found in the atom. Let's go over the four main quantum numbers. Number one, principal quantum number, n. This tells us the shell or energy level of the electron. It is like the electron's neighborhood. The shells are often labeled K, L, M, N, O, or just by numbers 1, 2, 3, 4, and so on. The higher the number, the further the electron is from the nucleus, and the more energy it has. Number two, azimuthal quantum number, L. This one tells us the subshell or the shape of the electron's probability cloud. The possible values are S, P, D, F, corresponding to 0, 1, 2, and 3. So, for example, if n is 2, then L can be either 0 or 1, meaning the electron could be in an s or p subshell. Number 3, magnetic quantum number. This tells us the number of orbitals in a subshell and their orientation. It ranges from -L to +L. For example, in a p subshell, which L equals 1, there are 3 orbitals, because it can be -1 or +1. Each orbital can hold 2 electrons. Number 4 is spin quantum number. Finally, we have the spin quantum number, which tells us whether the electron is spinning in one direction or the other. The two possible values are 1/2 or -1/2. This gives us one more way to distinguish between two electrons that are otherwise in the same orbital. So, to sum up, electrons are described by these 4 quantum numbers. These numbers tell us everything about where the electron is and how it behaves, which is very important to understanding the materials, chemical, electrical, and optical properties. Now let's talk about electron energy states. Electrons in an atom does not just randomly float around. They occupy specific energy levels, which we refer to as shells. These shells are like layers around the nucleus, and within each shell there are subshells like S, P, D, and F. Each of these subshells can hold a certain number of electrons, and the electrons always tend to fill the lowest energy level first. This idea is known as Aufbau principle. Let's break this down using the most common example, hydrogen. The electron in a hydrogen atom sits in the 1s orbital because that's the lowest energy state available. This is in the K shell where the principal quantum number n is 1. Now, if we look at something like oxygen, which has 8 electrons, they would fill the 1s orbital first, then the 2s orbital, and then the 2p orbitals, which belong to the L shell where n equals 2. But what happens when we get to atoms with more electrons, like the third period of the table? This is where we see electrons filling the M shell, which includes the 3s, 3p, and 3d orbitals. As we go even higher in energy, the N shell with 4s, 4p, and 4d orbitals comes into play. Each of these energy levels has a discrete or specific energy value, meaning electrons cannot just exist anywhere. They have to be in one of these energy states. And because these energy states are fixed, electrons cannot occupy in between levels. For example, you cannot have an electron halfway between the 2s and 2p orbitals. It is either in one or the other. Another thing to keep in mind is that electrons are always trying to occupy the lowest available energy state. That's why when you add more electrons to an atom, they fill up the shells in a specific order, starting with the lowest energy orbitals and working their way up. Here is another question. What do you think happens when all the lower energy states are filled? Where do the remaining electrons go? So, the key takeaway here is that electrons are arranged in shells and subshells, filling the lowest energy state first. This arrangement influences everything from the chemical reactivity of an element to its physical properties. Now let's take a closer look at electron configurations and how they relate to the stability of different elements. What we are essentially doing here is mapping out where the electrons are within an atom, from the lowest energy levels to the higher ones, as we talked about earlier. For most elements, their stability depends heavily on whether their valence electron shell is completely filled or not. For example, let's start with hydrogen. Hydrogen has only one electron, and its electron configuration is 1s1. It means it has one electron in the 1s orbital, which is its lowest energy level. Because this shell is not full, hydrogen is quite reactive. It wants to either lose that electron or share it with another atom or become stable. Move on to helium and things are different. Helium has two electrons, 1s2. Here, the 1s orbital is completely filled, which makes helium stable and non-reactive. This full outer shell is what makes helium part of the noble gases, a group of elements that are very stable because their other electron shells are filled. As we move down the periodic table, we can see that electron configurations become more complex. Look at neon with an electron configuration of 1s2, 2s2, 2p6. Here, all the orbitals in both the first and the second shells are completely filled, making neon another stable noble gas. But what happens when we get to elements that are not noble gases, like sodium? You know, sodium has an electron configuration of 1s2, 2s2, 2p6, 3s1. Notice here that the 3s orbital has only one electron, which makes sodium highly reactive. It really wants to lose that extra electron to achieve a stable configuration like neon. This incomplete outer shell is what drives sodium's reactivity. When we look at larger atoms like argon or krypton, the electron configurations get even more interesting. Argon, for example, has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6. Because its outer shell is completely filled, argon is another stable noble gas. But why is not krypton as stable, even though its electron configuration seems more complex? The answer lies in the fact that krypton's valence shell is not completely filled, which makes it less stable compared to the noble gases with full outer shells. Valence shells that are only partially filled lead to reactivity because these elements are always seeking to either gain, lose, or share electrons to achieve stability. Another important point here is that while most elements want their outer shells to be filled or for stability, they do this in different ways by forming bonds, losing electrons, or gaining them, depending on their specific electron configuration. To wrap it up, understanding the electron configuration of elements helps explain why some are stable and others are reactive. Stable elements like the noble gases have full outer shells, while reactive elements are always trying to fill or empty their valence shells. All right, Let's back into electron configuration again, but this time focusing on valence electrons, which are the electrons in the other unfilled shells of an atom. These electrons are super important because they are the ones involved in bonding between atoms and largely determine the chemical properties of an element. So, what do we mean by valence electrons? Simply put, these are the electrons in the outermost shell that is not completely filled. When an atom's outer shell is full, it is stable and doesn't react much, like in noble gases. But if the shell is not filled, those valence electrons become available to bond with other atoms to form molecules and compounds. Take carbon, for example. Carbon's atomic number is 6, so its electron configuration is 1s2, 2s2, 2p2. That means in its outer shell, the second shell, it has 2 electrons in 2s orbital and 2 in 2p orbital. So these 4 valence electrons are the key to carbon's chemistry. Because the outer shell is not full, carbon tends to form bonds to share electrons with other atoms, creating everything from simple molecules like CO2 to complex structures like diamond or graphene. Another thing to remember is that the number of valence electrons influences an atom's ability to either gain, lose, or share electrons to achieve stability. For instance, carbon has 4 valence electrons, so it tends to share electrons, forming covalent bonds. On the other hand, sodium, with just 1 valence electron, tends to lose it easily to achieve a more stable electron configuration. Let's continue discussing electron configuration by looking at a specific example, iron, or Fe. Iron has an atomic number of 26, meaning it has 26 protons, and in its neutral state, 26 electrons. To understand its electron configuration, we fill the energy levels based on the principles, which tells us that electrons occupy the lowest available energy states first. So let's break it down together. K shell n equals 1 can hold up 2 electrons, so we fill it first, 1s2. Next, we move to the L shell, which n equals 2, which also can hold 8 electrons. We fill that next, 2s2, 2p6. Then we fill the M shell, n equals 3 here. Again, it can hold up to 18 electrons, 3s2, 3p6. That fills up the M shell. Now we are on to the 3D subshell. Here is where it gets interesting. 3d6, which means we have 6 electrons in the orbital. Finally, we fill the 4s subshell, 4s2. Putting it all together, the complete electron configuration for iron is this: 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2. So this tells that iron has 8 electrons in its outer shell, which means it's interesting in terms of its chemical properties. It can lose, gain, or share these electrons to form various compounds. Now, let's think about this. Why do you think having 8 valence electrons would make iron an element in reactions. So, to sum up, understanding the electron configuration of elements like iron helps us grasp their chemical behavior and reactivity. The number of valence electrons is key in determining how an element will interact with others, making it important in fields like material science and chemistry. Well, now let's talk about the periodic table, which is like a roadmap for understanding elements and their behaviors based on their valence electrons. You know, elements are arranged in columns, also called groups, where each column contains elements with similar valence electron structures. It means that the elements in a column tend to have similar chemical properties because they react similarly due to having the same number of electrons in their outer shell. Now, let's break it down a bit more. We have electropositive elements. These elements are keen to give up electrons to form positive ions or cations. For example, elements in group 1 like sodium readily give up one electron to become Na positive. Similarly, group 2 elements like magnesium will give up two electrons to form Mg2 positive. We also have electronegative elements. These elements are more inclined to acquire electrons to become negative ions or anions. For example, elements in group 17, such as chlorine, readily accept one electron to become Cl negative. Group 16 elements like oxygen will accept two electrons to form O2 negative. This trend continues with some elements willing to give up three electrons or more, while others will accept multiple electrons to achieve a stable electron configuration. Let's think for a moment. Why do you think it is important for elements to, either give up or get electrons? What does it achieve for them? So, we have also the inert gases located in group 18, which are special because they already have full outer shells. It means they typically don't engage in bonding with other elements, making them very stable and unreactive. So, to summarize, the periodic table is not just a list of elements, it's a tool that helps understand how elements behave based on their valence atoms, whether they are giving up electrons to form cations or accepting electrons to form anions. This behavior is what drives the chemistry of the elements. Hope you enjoyed this video. If you did, don't forget to like, drop a comment below, and subscribe for more. See you next time.